This is on page 31 in your booklet. Again, it's going to look at some things that you've already done before, like intersection of lines you did back in grade 10. But now we're going to look at how to find that intersection of lines if we used our vector equation of line. And we're also going to extend it into three-dimensional spaces and see what that looks like. So if you have a two-dimensional space and you have two lines in a plane, there are three possibilities. Possibility number one is those two lines are parallel and they never intersect. So how would you tell from a vector equation of lines if two lines are parallel? Well, you're going to look at your parametric equations and set up a system of equations to solve. And when you try to solve that system of equations, you end up with some sort of false statement that isn't true. So you try to solve it and you get, oh, 5 is equal to 7. I never knew that. Doesn't make much sense. And that's telling you those lines aren't going to intersect and those lines are parallel. So here is an example to see what that looks like. We've got two vector equations of lines. If we look at the parametric equations for R1, we would have our x coordinates are 1 plus 3t, and our y coordinates are 2 plus 2t. For R2, our x coordinates are 2 plus 6s, and our y coordinates are 3 plus 4s. Putting these together gives us two systems of equations. It says that 1 plus 3t, if the x coordinates are the same, would equal 2 plus 6s. Supposed to be s there. And looking at our y coordinates, it means that 2 plus 2t is equal to 3 plus 4s. There's a system of equations. In our black there we have two equations with two unknowns. We don't know t, we don't know s. So we can attempt to solve that using any technique that we would like. If you want to use elimination, you can. If you want to use matrices and set up a matrix equation, you can. If you want to use matrices and set up an augmented matrix and solve it, you can. If you want to use elimination, did I say already? Substitution, elimination, or matrices, any way that you would like, you can to solve that. So what would you like to use? If these lines intersect, then the y coordinates would have to, there would be a point where the y coordinates are the same, and a point where the x coordinates are the same. And if that's the case, then there has to be a t and an s that does that. So if I use the elimination technique, I'm going to call this equation 1 and this equation 2. I'm going to take equation 1 and I'm going to multiply it by 2 and rewrite it here. So that would give me 2 plus 6t equals 4 plus 12s. And if I take my equation number 2 and I'm going to multiply it by a negative 3, my idea here is I was looking at my t values and I tried to get my coefficients of t the same, but one positive, one negative. Because then if I use elimination, I could just add them together. So when I multiply by negative 3, I'm going to get negative 6 minus 6t equals negative 9 minus 12s. And when I add these equations together, sure enough, my t's go away, which is what I wanted, and I just have negative 4 on the left-hand side. But unfortunately, my s's also went away, and I get a statement that's not true. Negative 4 is not equal to negative 5, last time I checked. And so, in this case, we know that the lines are parallel. Other ways that you could show that lines are parallel is you could look at your direction vectors. Can you see that these direction vectors are basically the same? They have the same slope of 2 over 3. So looking at those direction vectors, since one is just a multiple of the other one, that's telling you that they have the same slope. That's telling you that they are parallel. It could be that they're parallel and don't intersect, which is what we have because we got a system where the two answers didn't make any sense. But it could have also meant that they're parallel and the exact same line. That could also happen. And we'll look at that in our examples coming up because that's another possibility. If that was the case and you went to solve it, you would get a statement that was always true. Like 5 is equal to 5. Or 8 equals 8. Then you know that they're parallel and they're exactly the same line. Parallel, wow. How did that happen? There we go. There it is. Parallel, not parallel. Ooh. Okay. The most common thing that happens is you have two lines with different slopes, and those lines end up intersecting, and then they ask you to find where's the point of intersection. Say a name for this is concurrent lines, and we set up our system of equations as before, but this time we'll be able to solve for S and solve for T. And once you've got S and T, you can find the exact intersection point with that. So what does that look like? Well, again, we're going to set up our parametric equations. Here's R1. I'll color code it like I did before. So I'll do R1. The x coordinate would be -3 plus t. The y coordinate would be 5 plus 2t. R2, your x coordinate's 4 plus 3s. Your y coordinate is 3 minus 2s. Putting those together, we get -3 plus t equals 4 plus 3s and 5 plus 2t is equal to 3 minus 2s. So again, by equating your x coordinates and equating your y coordinates, you get a system of equations with 2 equations and 2 unknowns. So if you want to use elimination, I could multiply equation 1 by a -2. That would give me 6 minus 2t equals -8 minus 6s. Equation 2, I'm just going to rewrite. See what I'm doing? I'm using my elimination technique. I got my coefficients in front of t to be the same, but one is positive and one is negative. I like doing that because I find you make less mistakes when adding than when you do when subtracting. So now I just need to add 6 plus 5, that's 11. Sure enough, my t's canceled out. -8 plus 3 is -5 minus 8s. Add 5 to both sides. Divide by -8. And you get s is equal to -2. Since we were able to solve for s, now you could plug that value of s into either equation 1 or equation 2. And you will get the same value for t. So if I plugged in -2 for s into equation 1, I would get 4 minus 6, add 3 to both sides. I would get t is equal to 1. And I would have got t is equal to 1 also had I plugged in -2 into equation 2. Now that you've got S and T, you can find the point of intersection by either using our original vector equations. You could put 1 in for T. If I put in a 1 in for T, can you see that negative 3 plus 1 is negative 2, 5 plus 2 is 7. And so my point of intersection is negative 2, 7. Had I done the same thing with S as negative 2, so I put in a negative 2 for S, 4 minus 6 would give me negative 2, 3 plus 4 would give me 7. So negative 2, 7 is the point of intersection. You wouldn't have had to plug it into both equations, but I like to do that because if I get the same answer, then I know I did something right. If I get a different answer when I plug in my different values, something went wrong along the way. Maybe it happened right at the end. I check my addition right at the end again just to make sure. If not, I probably made a calculation error in figuring out S or T earlier. And the last possibility in 2 dimensions is you have 2 parallel lines that are exactly the same. These are called coincident lines. So they're right on top of each other. You will have an infinite amount of solutions. So how do we determine that? Again, what I've set up here is sort of like a system that you can start the same way with all 3. Because often you don't know which system you have, if they're concurrent lines, coincident lines, or just parallel lines that don't intersect. So if you set up your system of equations, and this one, when you try to solve it, you get something that's always true, 15 is equal to 15, that would tell you those lines are the same. So here's our 2 lines. First of all, a quick look. Can you see that the direction vectors are basically the same? One's 3, 2, one's 6, 4. Both of those would have slopes of 2/3. So that already is telling us that these are parallel. But if we wanted to find out, are they parallel and don't intersect, or are they parallel and exactly the same line, well, then we'd have to do some work. So if, again, color coding things, I look at my first equation line, my x coordinate will be 1 plus 3t. My y coordinate is 2 plus 2t. And the second equation, x coordinate is 7 plus 6s. Y coordinate is 6 plus 4s. So here's our 2 equations from that. 1 plus 3t is equal to 7 plus 6s, and 2 plus 2t is equal to 6 plus 4s. Again, I'm going to call this equation 1 and this equation 2. So let's say I'm going to use my elimination technique. I decide I want to get rid of my t's. So I'm going to take equation 1 and multiply it by 2. And I'm going to take equation 2 and multiply it by a negative 3. That way my coefficients in front of t will both be 6. One will be positive, one will be negative. Negative 6 minus 6t equals negative 18 minus 12s. And since we already knew that it was parallel based on the direction vectors, it's not surprising that both our t's and s's are going to get eliminated. But this time, 2 plus a negative 6 is negative 4. 14 plus a negative 18 is negative 4. I get the statement that negative 4 is equal to negative 4. And because of that, which is always true, what ends up happening is we can say that these two lines are exactly the same, because it's always true. What would happen if you set up your matrices? So I'm going to rearrange these equations. I'm going to, equation 1, are you okay with me writing equation 1 like this? 3t minus 6s is equal to 6. Are you okay with equation 2 becoming 2t minus 4s equals 4? Put this into your calculator as a 3 by 2 matrix. 3, 6, 6, 3, negative 6, 6, 2, negative 4, 4, and rough it. See what happens. What do you think's going to happen? So if you tried to get that into reduced row echelon form, what happens? Oh, wait, can you see that on the screen? Should I turn on a light? Ooh, and then you just got to tilt it so the reflection is just perfect. Nice. So you get a bunch of zeros. In a sense, that means one of the equations is 0 equal to 0. The same kind of thing where we got negative 4 equals negative 4. But if you had used this technique to try to solve it, reduced row echelon form, you end up with an equation, one of them that's 0 equal to 0. And this is how you would tell from there that these two are coincident lines. And they're exactly the same. Now, in 3 dimensions, we have a new thing that can happen. So if we're thinking about lines in 3 dimensions, you could have the same thing. You could have them intersect at one point. You could have them parallel. You could have them coincident, where they're exactly the same. But you could also have them that they're not parallel, but don't intersect. And the example that I have here is, imagine 2 airplanes, and they're flying through the sky, and sometimes you see like the little white trail that the airplane leaves. You could have 2 planes flying in different directions, but they don't have to crash into each other. Or they don't even have to have their like smoke trails intersect. I don't know if pilots ever do that. Do they ever try to run into somebody else's smoke trail just to say? No, I have no idea. Probably not. So you could have 2 planes flying in different directions at different altitudes. They're not going to crash into each other, but they're not flying parallel to each other. What's that? Water vapor. What did I call it? Smoke trail. I like that, smoke trail. So we're going to see, are these 2 lines concurrent? Do they intersect? And if so, find the position of their point of intersection. This is still in 2 dimensions. I'm going to get you to try this, since we don't know. Here's the solution. If you would have solved for it, you should have got lambda is 4 and t is negative 5. If that didn't happen, oh yeah, there's your mistake. And then 3, 8 is the point of intersection. And I've written it twice there because I checked it twice. I checked it by plugging in 4 for lambda, and I checked it by plugging in negative 5 for t, and ended up being the same thing. So once I have like this, then I go back here and put a 4 in. And then say negative 5 plus 4 times 2, that gives me 3.
No, sorry. I meant like you have one of the variables and you're trying to find the other one.
Once you have one of the variables and you're trying to find the other one, you can take either equation 1 or equation 2, it doesn't matter which one. And I found t is negative 5 first, but then I substituted negative 5, and I used equation 2 here, in for t, and then there was only lambda to solve for. So off to the side here, this would have been your regular vector equation of line. It's written with your unit vectors I and j. So whatever's in front of the I, that's like your x, and that's why we get x is equal to 3 plus 2s. And whatever's in front of your j, that is, and this is R1, and this is R2. And if you want to check if you got the rest right, oh, we get 11 equals 11, or maybe you got a different something equals a different something. These are the same line. Now looking back at the original, can you see that the direction vectors are the same? I mean, they're just multiples of each other. If you multiply 2, -1 by -3, you get 6, -3. So we know that these would have been parallel. The fact that when we go to solve it, we get something that's always true means that these are coincident lines, and they are the same line. Now we're dealing in 3 dimensions. So our direction vectors, maybe looking at them, if you multiply one by another, you don't get the same. They're not parallel. We can't get one direction vector, the 1, -1, 1, to equal 2, 3, -1 by just multiplying by something. So there's a possibility these lines intersect, or there's a possibility these lines are skew. So how do we determine that? Well, same way as before. We set up our parametric equations. Here, for R1, we'll have 3 of them now. Our x-coordinate is 2 plus t, our y-coordinate is 1 minus t, and our z-coordinate is t. For our second line, our x-coordinate is 3 plus 2s, our y-coordinate is 3s, and our z-coordinate is -1 minus s. And so from these, we get 3 equations with 2 unknowns. We'll get 2 plus t equals 3 plus 2s. We'll get 1 minus t is equal to 3s. And we'll get t is equal to -1 minus s. So I'm going to label these equation 1, equation 2, equation 3. Now when you have 2 things that you want to solve for, you only need 2 equations to do that. So if I want to solve for t and s, I only need to use 2 of those equations. It doesn't matter which 2 you choose. You could pick 1 and 2, 2 and 3, 1 and 3. Those would be your 3 options. When looking at them, though, when you choose, I often try to choose one where I think the math would be the easiest to work with. I really like equation 3 because t is already by itself. So I can use substitution here really easily to solve for this. So which equation would you like to go with 3? Equation 1 or equation 2? Equation 2? So if you use equation 2 and equations 3, and you decide I want to use substitution, I can start writing equation 2, but instead of writing a t, I'm going to write -1 minus s. That's equal to 3s. So this is going to be 1 plus s equals 3s. 2 is equal to 2s. S would equal 1. And if s is equal to 1, if I want to find out what t is, I can plug that back into equation 2 or equation 3, and I would find out that t is equal to -2. Can you see that that is true for equation 2 and equation 3? When s is 1, t is -2. Both of those equations work. But in 3 dimensions, that's not enough to say that's the point of intersection. we still need to check equation 1. What happens when s is 1 and t is negative 2 in equation 1? Well, if t is negative 2, I would get 2 plus negative 2 on the left side. And on the right side of the equation, if s is 1, I would get 3 plus 2. If we look at that, the right side is 5, the left side is 0. That's not true. So these are skew lines. If it were true, if you checked equation 1 and s and t worked for equation 1 as well, then you could find the point of intersection by plugging in s equals 1 into your equation or t equals negative 2 into your equation, and you would get a common point.